All right, so we're going to start electrons and light this unit. The law of conservation of energy. If you've ever seen one of these Newton cradle ball and string things where you pull the ball from one end and then on the other end it'll transfer the energy and it'll make the other end go up. That is hopefully describing how energy cannot be created or destroyed, that it changes forms. What that will occur for us here is the electromagnetic spectrum. We're going to be looking at different waves and their energy, their wavelength, and their frequency. So this is a good image that covers how the waves in radio waves are long and how the waves are much shorter in the gamma rays, and how where visible light sort of falls into this whole thing. This is the recommended spectrum that we'll be giving you. So similar in that, you know, visible light only takes up a small portion. All right, so it's only a small portion of the entire spectrum that they're showing. And I went and colored these in for you so that you could still have all the glorious picture that you have in that one. So, all right, so we were going to get into some parts of a wave. And before we did that, we played with this thing. And what this thing was showing us is that at a high frequency, let's start with a high frequency. Okay, if we freeze it there and we put out a ruler. So at a high frequency, the wave is measured from where it starts to the point where it's back where it started. So here it's going down from the center line. It's going up by the center line, so that's not the same point, and then it's going down at the center line. So that would be a full wave. So a full wave is going to measure somewhere about 2.5, 2.6 centimeters in this case, and that's with a higher frequency. If we lower that frequency, um, then we see that, well, that may be too low actually. Let's give it a little more than that. All right, so here we see when we start here, we go down, we go up, and then here. So that's almost 6 and 6.2, 6.3 centimeters. So a significantly longer wave when the frequency doesn't happen. Now, frequency deals with this going up and down, right? It is not necessarily the speed at which the wave is traveling. It's just the speed at which this thing's going up and down. That tends to be a little confusing to people. When we talk about speed of a wave, those are constant. So let's get back to this. So there's a wavelength, as we described, that's measured in meters. It's very important. So you can go top to top. So the top of one to the top of the next one. You can go bottom to bottom. So the trough to the next trough. What we typically do in science, though, is we will sort of mark it like a sine curve. So it goes up, it goes down, and then it goes back up to the center line. That's usually what scientists measure as a wavelength. But you can go top to top or bottom to bottom, whatever you want. Frequency is measured in hertz. Hertz is the same as waves per second, or ultimately uh, 1/seconds. And when you multiply wavelength times frequency, what you will get is the speed of light. So there are some constants that you're familiar with. Pi is a constant, and the speed of light is a constant. And as you can see here, meters per second. So if you multiply meters times 1/seconds. So when you see frequency times wavelength, we'll get back into this, is equal to that speed of light. Okay, because meters times 1/seconds equals meters per second. So the speed of light is a constant. It's 3 times 10 to the eighth. So no matter what light we're talking about, it's going to run at 3 times 10 to the eighth meters per second in a vacuum. In air, it's a little slower because the air slows it down. In water, it's a lot slower, but we won't get into that. There's also a thing called Planck's constant we'll talk about in this unit. The idea of a constant is that it can be limiting. So if you can only hold 48 M&Ms into this plastic egg, then if you wanted to add any more M&Ms to that egg, you would have to take some out. if that makes sense. If 48 is the maximum number of M&Ms that can hold in that egg, then to put another color in there, for example, you'd have to take some out. And so that's illustrated here. Now we have two colors, but we don't have 48 of one color. We have 24 of each color. And then if we wanted to put even more colors, the colors here, we had to take some out. Now we only have 16 of each color instead of 24. If we wanted to take 4 colors, now we only have 12 of each color instead of 16. So every time we add a color, we can't have as many M&Ms of that color because we're restricted by the fact that this egg will only hold 48 M&Ms. Because of that, if we were to graph this, the number of colors of M&Ms, as that goes up, the number of actual M&Ms in that color would go down. So we started with 48 M&Ms of green, and then when we had two colors, red and green, we could only have 24 of each, and so on. And the point of this is all these things equal 48 when multiplied. And that is the that's the limiting factor, is the fact that as these go up, these have to go down to counterbalance the fact that these are going up if they're still going to equal 48 when you multiply them. So that's exactly what happens when you have the speed of light and you're multiplying it by the wavelength and the frequency. Because that's a constant, because the speed of light is always 3 times 10 to the 8th, then when you multiply those two things, if one gets bigger, then the other one gets smaller. So we can see here there's a short wavelength for a high frequency, and there's a longer wavelength for a low frequency. So the wavelength got bigger as the frequency got smaller, and the wavelength got smaller as the frequency gets bigger. We call this an inverse relationship. As one increases, the other decreases. With energy, the kind of, well, it's a different kind of relationship. Now your constant, Planck's constant, is here. So it's not this times that equals the constant, it's this equals a constant times the frequency. So energy equals Planck's constant times the frequency. So therefore, this is a direct relationship, meaning as one goes up, the other goes up. So you can see here as the energy is the blue one, okay? So that will increase with frequency. So here's your energy, and here is your frequency. Okay, and as your frequency goes up, your energy goes up. And that's, think about it, if this is a constant, let's say it's 6, so frequency equals 1, energy equals 6. Frequency equals 2, energy equals 12. Frequency equals 3, energy equals 18. It keeps going up with frequency. They go up together because you're just multiplying whatever the frequency is by the energy, by the Planck's constant to get the energy. All right, now here's another way to think about this. If you had sort of a long wavelength, low frequency thing, and if you had, well, I guess I'll stay with that, sort of a high frequency, shorter wavelengths. All right, so let's say there's somebody out there that is in the water. So this is one of my children there, right? So they're screaming for help because they're in the water. All right, so which of these, no idea how that happened. Which of these, okay, which of these situations would one rather be in? Well, if I'm the one who's got to go swimming out to help said child, then it's much easier to swim in the situation of the top because the energy is not going to be as bad. It's sort of that rolling wave. It's not going to be pushing me back, whereas this one will. So let's put me over here. All right, and I got my new headphones, and I got this fancy haircut today. So yeah, and I'm just listening. Hopefully I can hear the help. But if I got to swim, I should get some arms so I can swim. All right, so if I got to swim there though, this is a much easier swim. It's the energy is not pushing me down, whereas this, think about it, the waves are just battering me back to shore. All right, so this has higher energy and this has lower energy. And hopefully that makes sense. If it doesn't, there's another way to do this. There's yet another way, and that's here. You know that X-rays and ultraviolet and gamma rays are bad for you, right? X-rays, when you go to the dentist, they put that lead vest on top of you. Ultraviolet is why we wear sunscreen, so we protect against the cancer that ultraviolet rays cause. Gamma rays, right, that cause a Hulk. That's how Hulks get to be. So, not sure how that's a Hulk. It's starting to look like a Hulk. I don't know. I think I went a little Frankenstein there. But anyway, so gamma rays do that. These are all the dangerous ones. These are the high energy ones, right? Whereas radio waves, you can listen in your car to the radio without having to put on a lead vest. Microwaves are how your phone works. You don't need a special helmet to answer your phone. These are not as bad, lower energy. So this is low energy, just based on what you know about the names, right? And then visible light, of course, isn't that scary. All right, so let's do some of these problems. So ultimately, the equation is that the speed of light is equal to the wavelength, which needs to be in meters, and the frequency, which needs to be in hertz. So what we have here given is a wavelength. All right, so we have 4.10 times 10 to the minus 7 meters, another indication that's meters, right? We're looking for the frequency. So we're looking for this, and what we have is the speed of light, and the speed of light is always 3 times 10 to the 8th meters per second. So what we need to do is then put this into our calculator. So we're going to keep this, and I'll show you a calculator on Google. So if we're going to do this on a calculator, you can't use the 3 times, well, you can. You could say 3 times 10, and now this doesn't have a raised to the x, I don't think. I'm not seeing one, but then you could put the caret and to the 8th. The problem with using this is the calculator thinks that's two different numbers. And as we've discussed in the past, when you do that on a calculator, so ultimately what we're going to do here is divide 3 times 10 to the 8th by the wavelength, 4.10 times 10 to the minus 7. If you don't put this in parentheses when you do it that way, it's going to take that times 10 to the minus 7 and put it back in the numerator. And that's not good. So to avoid that, what we're going to do is in the calculator, we're going to use this E button. So we go with 3, and then you would have an E. This is an EXP. 3, and that means times 10 to the, and we're going to use eighth, and then we're going to divide it by 4.1 E, which means times 10 to the, and then real quick, minus 7. So on this calculator, you use this as a negative. There should be a plus minus button on most calculators that you would use in this case, but on a Google calculator, you just hit minus 7 like that. So it's 3 times 10 to the 8th divided by 4 times 10 to the minus 7. And you hit equal. So now the calculator didn't need you to tell it that was one number. It kept it all together. If that was 4.1 times 10 to the minus 7, you would have had to put that in parentheses. If you use the E, you don't have to. So your answer is 7.32 times 10 to the 14th. So getting back here, this equals 7.32 times 10 to the 14th. And the units of that are hertz, or 1 over seconds. So meters over meters per second, that should make sense to you that this is meters per second, and this is meters, and the meters will cancel, and you'd get 1 over seconds, which is what hertz are. All right, another way to make sure you're doing your work when you're subtracting, when you're dividing exponents of 10, 10 to the 8th divided by 10 to the minus 7 would be 8 minus a minus 7, which equals 15. So you should be in the ballpark of 15. And the reason that happened is when you divide 3 by 4.1, you get 0.732 times 10 to the 15. And when you move that decimal over there, you account for it here to make it 7.32 times 10 to the 14th. All right, and what region? I didn't even answer the first question. What region is this? So 10 to the minus 7 is where you're looking on your spectrum here, 10 to the minus 7. It could be ultraviolet, but it's 4.1. Notice all visible light is 10 to the minus 7. So make sure you look down here when there is a 10 to the minus 7, and 4.1 falls between 4.0 and 4.2. So the answer there is it's turning violet. There you go. All right, another sample. This is an X-ray, and it has a frequency this time. So we need to find the wavelength. Now, since we know it's an X-ray, our wavelength should be in this ballpark here, right? Something in the 10 to the 8th, 10 to the 11th negative. So we're going to use the same equation where the speed of light is equal to the wavelength times the frequency. Now, another way to think about this, if you like the triangle method, is that the frequency times the wavelength equal the speed of light. That's what we started. And that's because you will always divide the speed of light by one of the other ones. So speed of light divided by wavelength will give you frequency, and speed of light divided by frequency will give you wavelength, and then wavelength times frequency will give you the speed of light. So if we put everything together here, our speed of light is 3 times 10 to the 8th, and then the lambda we don't know. We know ballpark where it should be because it told us of the x-rays. And then we have 4.76 times 10 to the 16 is the frequency. So again, as we just saw here, you will always divide the speed of light by whatever's given, basically. And in this case, what's given is the frequency. And checking our work, 8 divided by 16 should be a ballpark -8. So we go to our calculator, and we get 3 exponent 8 divided by 4.76, and that's exponent 16, I think. 16. There you go. And that gives you 6.3 times 10 to the minus 9. So that is the answer. 6.3 times 10 to the minus 9, and that falls within the range we were thinking. And the units of that, again, are hertz. So that would fall into there. So what we're going to do now is just a couple real quick things to think about. If I asked you which has higher energy, orange, okay, or infrared, so which has higher energy? The high energy things are on this side of things, right? Here's the highest energy. Oops, I don't know why I'm writing like that, but okay. Just had a mini stroke. It's okay. Um, this makes no sense at all. This is high energy on this area, and this is low energy in this area. So infrared is closer to the low energy than orange, which is in this area here. So the higher energy is orange, and the lower energy is infrared in that case. Okay? So another example, if I said which had the greater frequency, so higher, oops, I should have put that in blue, but I'll put this in blue, higher frequency. And if we're looking at blue or yellow, right? Blue is closer than to yellow, closer to the high energy things than yellow is. And the high energy things have high frequency, and the radio waves have low frequency. So therefore, blue would be more frequent than yellow because of its proximity to the shorter wavelength things on the spectrum. All right, now we're done. Hope that was helpful.